Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. So we are continuing with discussing regarding topic of week number 5. As I mentioned in our previous lecture, shown here the steps that we're going to adopt in learning regarding issue of week number 5. So the first task that we put aside is to talk about current. So we have done that, and we end with discussing 3 model equation of current. So from there, we're going to go to the second step, which is to talk about conductor. Okay, so this is what we're going to do now in this session. We try to complete everything within this one session if possible. If too much, I'm going to split into 2 lecture sections because I don't want it to be too cramped in one video session. And I know that the things that need to discuss regarding this part is a lot. So let's make it based. Let's do what based on what we going to have later on. If too much, we're going to split into 2 different lectures. If you can cope, you found it to be easy, we're going to just do it in one session. Okay, so the topic of discussion that we're going to do now is talking about conductor. Okay, that's what we're going to focus on. We want to discuss issue regarding conductor. Okay, so for those who have already bought the textbook, so you can refer to section 5.4. So I'm going to write it here as a note, 5.4, and then the page number is 184. Yeah, so what I'm going to discuss now is quite relevant to the information provided by Sadiku in his textbook in this particular section. So what we're going to do now, let's go back to the principal idea that we put forward when we want to discuss about material. Okay, so when we want to talk about material, what's important, the discussion must involve 3 major components. So the first component that we must have should be the actual material. So let's make it to be this red box. That should be our conductor. Okay, so I'm going to put number now just to make it easier for you to understand what I'm trying to say. So the first component of the discussion always be the actual material. So in this particular discussion, the material should be represented as a conductor. And let's imagine this structure is part of a complete circuit. So let's make a note here. So what we draw here, so this is part of a complete circuit. So part of a circuit. So meaning that actually there's a link to this material to a part of the circuit, and this side of the conductor also linked to another part of the circuit. So meaning it's a actual part of a complete circuit. So that's what we try to imagine now. I'm going to draw a dotted line here to indicate to myself the material of discussion here is part of a circuit. So that's done. So the second important component should be put forward is the applied field. So let's draw the applied field as such. So this is our applied field. Since the topic of discussion here involves electrostatic, so therefore we are going to assume our applied field in this particular scenario is E field. Okay, because that is the nature of the discussion. So we are still in the world of electrostatic. Therefore, we are assuming the field that being introduced to the conductor is an electric field. So that's number 2. And number 3 should be the charged particles exist in the material. So let's draw the charged particle as this black circle. There's a lot, and let's ask ourselves, what is the majority carriers appear in the conductor? So anyone want to answer what should be the majority carriers in a conductor? So therefore we're going to say this number 3 will be known as electron. Correct? Because electron is the majority carriers that exist in a conductor. So therefore that should be number 3. Okay, number 1 again, the actual material. Number 2, the applied field. Number 3, going to be the charged particle exists in that material. Then what we need to do now, we need to ask ourselves, what happened to this electron when electric field been introduced to it? Because electron actually a charge, but the magnitude of the charge is in the negative form. Yeah, so therefore still a charge. And we know that when a charge been introduced to an electric field, there's going to be force created, and the force will cause that charge to move. Okay, therefore similarly here, what happened to this electron? It will move. Okay, since this particular structure is a part of the circuit, so therefore you can see the electron will move to the outer part of the material, meaning it's going to move into the circuit itself. So now we know that the electron will move, but in which direction you think that this electron will move? Okay, good. So this electron will move in the opposite direction to the electric field. So therefore we're going to denote the movement of electron in this direction. And there's a name given to this movement of electron. We call this velocity as UD. Okay, U stand for velocity, D stand for drift. So for conductor, the velocity is given name as drift velocity. Okay, so what it meant here, the electron is going to move very slowly. Why? Because there's a lot of electron in this region. So every time the electron appear to move faster, it's going to collide with the neighboring electron, causing it to release heat. So therefore, in a general term, we are saying to ourselves, this electron moving in a very slow motion. Then therefore, the name drift been introduced. Okay, so what we are saying now, the electron going to be moved in opposite direction to the E applied, and the name given to the velocity is known as drift velocity. So let's recall model current equation number 1. Recall, okay, model current equation number 1. Let's recall that equation number 1 that we introduced in the previous lecture. So we know that the J should be equal to rho V U. Remember that equation that we developed? We call this equation known as convection current density. Okay, so now let's adapt this equation for our scenario now for conductor. Okay, for conductor. So we are going to say now the J going to be equal to rho VE. Why we denote it to be rho VE? Because we are going to say to ourselves, this is electron charge density, rho VE, because electron charge density, and the value of this charge value should be negative because electron having negative value. So therefore the rho VE must be in terms of negative value, and then we know that the U should be denoted as U drift to indicate the movement in a conductor. And actually the component that affecting UD, okay, and UD, okay, actually can be defined as, first, must be the electric field, correct? When there's electric field, it's going to have the creation of movement. Without electric field, no movement to the electron. Therefore, for UD to appear, there must be electric field introduced to the conductor. But what we can observe, the direction of the UD is opposite to the direction of E. Therefore, I'm going to denote it as minus E. Okay, that should be the first component relate to the definition of drift velocity. And the second parameter that important in defining UD is known as mu E. Okay, what mu E stand for? This is known as electron mobility. In other words, how easy the electron move in that medium. So different conductor will have different value of electron mobility. For example, gold going to have different value of electron mobility when we compare to silver. So meaning that this parameter is indicator how easy for electron to flow in the given conductor. So that should be the parameter needed to define drift velocity. And then when we substitute UD into equation, finally what we're going to have, so what we're going to have here, the J should be equal to, so we're going to substitute UD into the equation minus rho VE mu E multiplied with electric field. Okay, and then as what we are expected in our discussion, we should introduce important parameter in conductor. So this term actually is known as conductivity. So you can see conductivity actually involve two major parameters. First, the charge density. Another parameter is the electron mobility. And then the sigma we used to represent conductivity should be small sigma. And the final equation that we are introducing here, okay, so now the final equation that we are putting forward in this particular discussion is J equal to sigma E. Okay, so the name given to this equation is Ohm's law in point form. Okay, the one that you see Ohm's law in circuit theory is not in point form, in a bigger form. But in this particular equation, this is still an Ohm's law, but it represents a point form, a very minute situation. And we also define this equation as conduction current density. Okay, so now we have been introduced to the second type of current density, conduction current density. From the name itself, we can deduce this current only appear in a conductor, whereby convection current density can appear in any medium, regardless any medium. So now for the second current density that we've been informed here, only dealt with conductor medium. Okay, so this should be the second type of current density that you're going to see in this particular subject. Okay, so let's talk about this conductivity issue. So if you refer to the textbook, okay, so if you open page, okay, refer to, let's say, page 847 of our textbook, and you will see there's Appendix So the appendix given here is Appendix B. So this appendix is actually a tabulation of material with their respective conductivity values. For example, for gold, the sigma is given as 4.1 times 10 to power of 7 Siemens per meter. Unit for conductivity is Siemens per meter. And another good conductor that used a lot in engineering applications, especially electrical, is silver. The sigma here 6.1 times 10 to power 7 Siemens per meter. Okay, so you can see now, sigma is an important parameter to define the standard of conductor material that we are dealing, the quality of the conductor material we are dealing. For a good type of conductor, the value of conductivity should be very, very high. And let's say we take example now, silicon. So silicon is a typical material that we use a lot in semiconductor application. The sigma here, given by the table, is 4.4 times 10 to minus 4 Siemens per meter. And you can see from the value compared to the one shown above, it's much, much smaller. So therefore, silicon is assumed to be not as good conductor if compared to gold or silver. And let's take example of a typical dielectric. Let's say glass, for example. So glass, when you take glass, the sigma value is 10 to minus 12 Siemens. So from there, we can see glass is a very bad conductor, and then it's also known as a good dielectric. Okay, so let's talk about application of this material. So let's talk about transmission, power transmission. So let's discuss application now. Application that utilizing conductor material. So we're going to, for example, in this case, power generation. Okay, and a company that well known in Malaysia to transmit power from the generator to the customer is known as Tenaga Nasional Berhad, so TNB. So let's draw a typical transmission power that TNB has. So usually you always see there's a big tower, okay, and then another big tower. So the distance depending on the capacity of your voltage, so usually maybe 50 to 100 meters, so let's make it 100 meter. So attached to this particular tower, you're going to see a lot of cables being laid out. So this is a typical scenario of transmitting power from the power generator to individual household in Malaysia. So if you've been asked to draw the equivalent circuit of such structure, so let's draw the equivalent circuit now of such structure. Okay, the equivalent circuit. What should be the equivalent circuit for this equivalent circuit of this structure? So usually what you're going to see to represent the structure will be this circuit. It consists of one component, okay, and then it's going to be another parameter involved there, and then what you're going to have it handy another parameter drawn like this. So that is a typical equivalent circuit used to represent this particular structure. Okay, so this is a per unit diagram, and then we know that this particular component is known as resistor, and then we know this as inductor, and this last component we call it to be capacitance. But then we ask ourselves, do we have a resistance per se in this particular transmission line? Okay, so meaning that this resistance actually a component contributed by the cable itself. Okay, so the cable actually made of a material known as good conductor, and when you deal with a conductor, you're going to have a parameter known as sigma. Okay, due to the reason why we are using conductor material, therefore that situation will introduce a parameter known as resistance. So the resistance appear here is not due to we are placing a resistor in the circuit. No, it's actually the reason why is here because we are using the cable made of conductor. So in other words, whenever we use a conductor material, that situation will introduce a parameter known as resistance. Okay, whether you like it or you don't like it, whenever we use a conductor material in our application, in our design, that situation will force us to introduce a parameter known as resistance in our application. So logically what we're going to do now, we're going to determine this resistance. Okay, how we actually calculate the resistance here. And then you have learned about this method, finding resistance using in circuit theory using Ohm's law. But in our scenario here, we are going to calculate resistance using another method. We call it to be field theory approach. Okay, therefore, what we're going to do now, we're going to find resistance. Okay, using field theory. So that should be our task now, because we've been informed whenever we use conductor material, that will introduce a parameter known as resistance. So we're going to calculate the resistance using a method known as field theory. So we don't have to have a power supply, we don't need to have a voltmeter. What we need here just a pen, calculator and table. So for us to find resistance. So it's very practical in the engineering field when you are trying to find the resistance value of a given material. Okay, so let's talk about this now. We know from circuit theory. Okay, we know Ohm's law said okay, so V equal to IR. And from here we can determine the resistance R equal to V over I. Okay, correct? But what we're going to use to find the resistance here, not using the ordinary method in circuit theory, we're going to use field theory. And we know that from field theory that we learned before, how we determine potentials. Anyone recall how we determine potential from our previous lecture? Okay, we know that the V can be determined by using the formula V equal to minus integration of E dot dl. Okay, so that's the name of field theory. So we are using electric field to determine the resistance. Therefore, the first logical thing that we need to do to replace the V with this equation that we have defined when we talk about potential. So therefore, that should be the first substitution. Logically need to be introduced to find the resistance. And for the current, and then this current will be defined as conduction current. And we know that from our second model of current equation, recall that the I is equal to the integration of J dot ds. Remember that equation? Equation number 2, what we developed regarding the current. current is equal to current density multiplied with the sample area. So now, since we are dealing with conductor, the current here should be conduction current. So for conduction current, what should be the J needed to be replaced here? Okay, and the J, as what we shown or proved earlier, in a conductor is given as J equal to sigma E, correct? So now we're also able to convert the I in terms of electric field to fulfill the requirement for resistance using field theory. So the actual equation that we need to use, okay, using field theory is that the resistance now, okay, it's not the vector, it's equal to minus the integration of E dot dl. We divide everything with the integration of sigma E dot ds. That should be the method that we use to find resistance using which theory? Good, field theory. So this is going to be the appropriate equation we use to determine resistance of any given conductor material. Okay, so let's do one example to investigate this further. Okay, so let's do one example now. So example here. So let's say you have a conductor material shown as drawn here. So let's say you have this conductor material. Okay, red in color. Okay, so that should be the conductor material having conductivity. Let's make it to be, okay, so what should be the conductivity for this? Let's make it to be sigma. So sigma is the conductivity of the material. Okay, and then let's attach axis to this diagram. So let's say this side of the conductor is coinciding with the x-axis, whereby this side is coinciding with the y-axis. Okay, so let's introduce the axis now. Okay, so this should be our z-axis. Okay, and then let's make it, so that should be, okay, clearer now. Okay, so that should be the axis of interest in our structure. So again, what we have now, a conductor dimension-wise shown here in the red diagram. This material having conductivity value as sigma, we don't have the specific value, just general representation because it's a conductor. Therefore, there must be a parameter given here, sigma. So let's give dimension to this structure. So let's say the thickness of this structure, let's make it to be C. Okay, that should be the, and then the inner radius of this structure, so this let's make it to be RA, R subscript A, and then the outer radius of this structure should be R subscript B. Okay, so therefore you can see much clearer now the structure having material parameter sigma and the dimension given as such now. So what actually the question all about? The question asks us to do this, find the resistance, okay, between surfaces z equal to 0 and z equal to C. So that's the question require us to solve here. What we need to do, we want to find the resistance, but between specific surfaces. So meaning that this problem can have an infinite resistance combination, but for this particular problem, we need to find the resistance between what? Between the bottom surface, Z equal to C, so that should be one reference surface, and the upper surface here, Z equal to C, before Z equal to 0, very sorry. So that should be our imaginary resistance that we need to calculate. So that should be what been asked for us to solve here. What should be the resistance between the bottom surface and the top surface of our structure? Okay, so that should be the task now, finding resistance using field theory. So how do I solve this problem? Okay, for me, when I want to solve this problem, again, I would like to determine the suitability of coordinate system. And from the structure given, we should agree by now, the preferred coordinate system must be cylindrical. Okay, so therefore, we're going to adopt cylindrical. Then I'm going to make it simpler by just redraw the problem in two-dimensional. What I meant by that, since the surface of interest are Z equal to 0, I'm going to draw now equivalent circuit Z equal to 0. Another important surface, Z equal to C, I'm going to draw Z equal to C. Okay, so why I'm going to do? I'm going to draw this part in my diagram, so in 2D now. So therefore the parameter needed to show this variance should be Z, and for this position 0 and this position C. So I want to find the resistance between these two. I'm going to assume the other combination surface not relevant in this particular situation. Since we are using field theory approach, logically we're going to introduce electric field. So now I want to introduce electric field in this dimension that I already built. So what should be the easiest way for me to represent electric field here? Okay, because we have to introduce it. Without this electric field, we can't proceed using this equation. The only way for us to use this equation must be able to imagine how the E should appear in this diagram. Okay, so therefore we need to imagine the field needed to be appear in this particular model. So we should think the easiest way. So for me, the easiest way is just drawing the shortest line joining the two planes. So what I meant by that, the shortest line will be this blue color now. 90 degrees, 90 degrees. That should be our shortest line, joining the two relevant planes. And this blue line actually are our electric field. And for us, electric field is a vector, so it must have direction. So I'm going to indicate my direction from bottom plane up to top plane. So you can choose the direction to be opposite, doesn't matter. Yeah? So it just need to be shown. So this should be my electric field. Okay, so now I can use this idea of E in my equation that we developed earlier. So now, but what should be the actual mathematics involved in the E? Then we need to ask from our previous discussion regarding generation of E, how this E can behave as such. Okay, so therefore this proposal must come with your experience. So for those who understand well about Coulomb's law and Gauss' law, you can see this logic. Okay, for me, to produce such E to be like that, we need to have these particular sources. What are they? They must be a positive surface charge appear at Z equal to 0. So I'm going to assume I'm introducing now rho S. And then as I can also assume now, there should be a negative charge appear on the surface of Z equal to C negative rho S. Okay, so I'm creating now, I'm suggesting now, because why? Because my experience allow me to propose this idea. because I need to substitute the E with this charge information in order I can use this equation. Okay, so this logical relationship must be well behaved. You cannot simply based on your interpretation, must come with fundamental concept, must be something that truthful. It's not something that you created based on hearsay. Must be something that come from our previous encounter when we dealt with with Coulomb's law and Gauss law. Okay, from this issue, I can know that, okay, so where I'm going to put now, okay, the E is actually due to the bottom source, okay, when we assume the structure to be like this, for our infinite surface charge problem that we solve together, we can say that should be rho s over 2 epsilon naught in z direction. That's due to the z equal to 0 charge. But we can also see there's another source up here, so it should be plus rho s over 2 epsilon naught z direction. So I'm going to write a note here so that you can see the logical explanation of my suggestion now. So I'm saying the first term due to rho s on z equal to 0 plane, and the second suggestion here is due to rho s, okay, negative rho s on the z equal to c plane. Okay, so therefore you're going to have this combination. So the summation of these two fields going to end with rho s over epsilon naught z. Okay, by doing this only we can have a definite definition of the E, and then this idea can be used in our actual resistance calculation later on. So you can see now it's very important your experience that you have encountered, you have built before when you are doing examples from Coulomb's law and also Gauss law problems. So this idea come in play logically. Okay. Now, so let's proceed, shall we? Hope that you not feel lost, even though it look a bit cumbersome, but if you think slowly, everything is not that difficult. Yeah? So now I'm going to go to the next level. So resistance now. Get resistance. Okay, I'm going to find the resistance now. This is the thing I'm going to do. So resistance, so the R should be equal to minus, okay, so first E dot dl. So what should our E? Rho s over 2. Okay, I'm going to put now, sorry, rho s over epsilon naught z directions. Okay, that should be the first substitution. Dot with my dl. Then I'm going to divide everything with sigma rho s over epsilon naught z dot with ds. Okay, that is the step that we have to do. So again, you can see the E come from our own interpretation. Yeah? So now I'm going to continue by talking about what should be the dl I need to put here. Okay, again based on cylindrical coordinate, the dl should be consist of dr r directions. What else? Plus r d phi direction and plus dz z directions. And when we do dot product, you can see logically the final result that you can obtain from this dot product will be only the dz. Why? Because the z dot r will give us 0. the z direction dot phi direction will also give us 0, but the only available or result that exists at the end of the dot product will be the z direction dot with the z direction with n with 1. Okay, how about the ds now? What should be the ds I'm going to place here? So this comes to our diagram that we have now. Okay, so we can see now the E field actually from bottom to top. And the way we define the ds, actually the sample area where the field is penetrating, that should be our ds. Okay, so that should be our ds. So how will this ds appear in our 3D? So you can logically say the ds should be in this form. Okay, what is it? So this should be depending on the r, dr, and this is going to be in terms of phi r d phi. So our ds here should be substituted with r dr d phi, but it's a vector, and then the vector must be normal to the area, and we know it to be in the z. Okay, that's how you actually substitute the dimension to the mathematics based on the actual situation you extract from our diagram. Okay, so let's solve the mathematics now. So what should be the limit of my z here? Yes, good. Based on the mathematics, the limit should be from 0 to c. So I'm going to make it in opposite direction from c to 0, because I want the outcome of this integration will be in positive form, because I want the resistance going to be n with the positive value. I don't want my resistance value to be in negative form, because that's going to be peculiar in ordinary circumstances. Okay, and for the second part of integration should be double. Why? Because it's surface. One will be based on the r, another one will be based on the phi. For the r, very simple, should be from RA to RB, and for the phi should be from 0 to be pi over 2. Why? Because our conductor material is extending from x equal to 0 into the y-axis. So it's extending from x-axis to y-axis. So at x-axis phi equal to 0. At y-axis phi equal to 90 degrees should be pi over 2. Okay, so let's solve the mathematics now. Okay, so let's do it now. So my r going to be, so I can cancel my rho s over epsilon naught. That's cancelled. So I'm going to end with what up here, going to be c only, because dz, c, divide everything. Sigma is still there. Then I'm going to multiply with pi over 2 due to the phi integration component, and then should be another one should be RB minus RA. Okay, because you integrate R here, should be R square, because R here, R square over 2. Correct? Because you have R here. When you integrate R, should be R square divided by 2. So therefore, R square need to be substituted with B, and also need to be substituted with RA. So you're going to end with this. So the final solution of this problem, R should be equal to 4C over sigma pi RB squared minus RA squared ohms. Okay, that's how you calculate the resistance using field theory approach. So what we learned before, finding E using Coulomb's law or Gauss' law is very important. Without able to determine the E from our previous method, we cannot solve this problem here, because for us here to find the resistance is important for us to know the E representation. Without that, we unable to do it. Okay, so let's do one problem. I'm going to leave you to do this yourself first. Hopefully, I'm going to explain this problem in my tutorial session later on. But if no one asking me how to do it, I'm going to assume you managed to solve the problem yourself. So what the problem is all about. So this should be your own exercise. Okay, this is problem number 1. Okay, say problem number 2. This to be done by during your own sweet time. Okay, so the problem number 2 is based on the same structure that we have just now. Find the resistance between surfaces R equal to RA and R equal to RB. That should be your task that you need to do if you want to. Okay, but if you try, you're unable to solve this problem, you can give a shout to me through WhatsApp or through email. Asking me to show you how this problem can be solved using the same method that we already been shown just now. Okay, so this is for you to do yourself. Maybe the same problem will come out in the quiz session, who knows, or in the test 2, so we do not know. Okay? So this is the thing that you need to look into and try yourself. But if you can't, doesn't matter, you can ask me. Inshallah, I'm willing to show you if that what you desired for me to do. Okay, so that's done. You think it's enough? At this moment, I think it's enough now. So I'm going to, as mentioned earlier, I'm going to split this session talking about conductor in 2 sessions of video. So inshallah, we're going to see each other again in our next lecture. So with that, I'd like to say thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.